Yeah, I've never seen a t-shirt before, so it's quite good.
Almost there.
Sí.
Sinzenia. So, yeah. See the next. As you see, you can see. No. Yeah. That's right. At the text, but there's something.
Yeah, it was, I mean, it switches more.
At the text is green. Right. Let's give it a try again. After the other. Let's see.
It's trying my computer.
Shit. No. Something else.
That's you. Okay.
Okay. Two. So let's try a different adapter.
Is it plugged in?
It's detecting the screen. So she's saying there's a second screen. So let's try this.
But that might only just because you plugged in.
Well, usually it's the office one.
Ja, aber es kann sein, weil du einfach den Stecker ins
Wir können,
musst du mir den Ja.
we don't have those laptops. You can. Yeah. But there's a bridge. Is it the need? Ist die Lampe gerade nicht geleuchtet? Mit diesem schönen Gerät, mich gerade nicht geleuchtet. No, but I think also on the switch the light was off. So maybe let's give it a try again.
Still not.
Project. No, now it works. This is going to.
Okay.
Thank you. And if it has to reboot and if there's power supply, it works. Oh. We're set.
Okay, good morning, everybody. Welcome to Rmcat. My name is Mia Kühlewind, and right next to me today is sitting Martin Stimmerling. And that's also the first announcements I'm going to make. So we will have in future 2 new shares. Anna is already on board for a while. Unfortunately, she can't be here. And then I will step down right after the meeting, and Martin will replace me. Right now. So, now it's you.
Yeah, as I said, like my name is Martin Stiemeling. I'm still one of the transport AD, but it's going to change this night So then Mia will be the new Transport AD, and I'm going to take over the co-chair position for her. So you're going to see me more often probably, and see me on the mail list more often. Thank you. So.
Yeah, and then also thanks to our note taker, Brian. And then we go on the next slide. Yeah, note well. Please note well what's written on the note well. This is stuff you might know as well. We have Meet Echo running. Rune is already waiting because he will speak later, and I'm also trying to monitor the Jabber in the Meet Echo room. Yeah. And then the working group status. So that's, unfortunately, I don't see the screen over here. It's a bit confusing. Anyway, so we have a number of working group documents. The first one, requirements, is just waiting for missing references, and these are not our references. It's from WebRTC, and it's a document that was supposed to be finished soon, but it's not. So it's waiting there for a couple 100 days already, but that's okay. And then we have the two documents here that are related to the evaluation itself. We will get a quick update from Arun and Sahid afterwards. They both have been updated recently, and there are minor issues to address here. Then we have the wireless test cases, which has not been updated recently, but we will see a presentation today. And we have the codec interaction, which was also updated recently based on feedback we got on the mailing list from reviews. Thank you for that. And basically, the framework document is more or less ready. However, there's text in the interactions document, sorry, is more or less ready. However, there's text in the document. We might move to a new framework document that's coming up. And then we have also the video traffic model, which was also not updated before the meeting, but I believe there's an update coming up soon, and we have a presentation about that. Regarding the algorithm candidates, we have seen a number of reviews over the last couple of weeks and months because we actually requested reviews at the last meeting. So those have been updated and worked heavily, and we are proceeding here to finalize them. The shared bottleneck detection document is also updated and basically ready, and we have a quick presentation on this afterwards, or at the end. And then couple congestion control is also updated and ready, and we have a presentation on this as well. Yeah, so we have a few documents which are not working group documents, and there's the FSC document. That document has been updated, and we briefly discussed this based on the framework document. I will tell you more later. And then there were also a couple of documents related to feedback, and we have a time slot also later to discuss these things. We're still waiting for a document on application interactions, which Varun promised to bring up soon, and then the framework document, which I mentioned a couple of times already now. I think Varun is only waiting for his own presentation. Yeah. Quick look at the milestones. So all the milestones here in red are expired, basically. Some of them we are close to finishing, but we have to update our milestones because we're not there yet. This still takes a moment, but I leave this to the new chair. So they will come back to you and update the milestones at some point. Yeah, so the framework document I've been talking about already the whole time. So this is an ongoing discussion we had over a couple of meetings already, and we had a quick side meeting this Tuesday morning and decided that we really need it and that we really want it. And so I guess Sahid and Xiaoqing have the pen at the moment to bring up a first version of this document, and all the authors of the candidate algorithms also agreed to align with this document afterwards. So we really need the document, the framework document first, and then we can update all the candidates. So that's like a high priority for us now. We also briefly discussed if we need to merge any codec or app interactions into this framework document, but we leave this question open for now, so those stay separate for now and then discuss this later. But anybody who would like to contribute to the framework document, please talk to Sahid and Xiaoqing. Then we chairs would be interested to get a better overview about which results have been shown for which version of which of the candidates, because we don't have a very good overview here. And we have the feeling that because all the candidates, all the algorithms have changed a little bit over the last couple of months and weeks, we would like to see some results again, because I guess you are running the test anyway every time you change something. So so the question is, how do we get an overview? Should we put a table somewhere, or do we just whatever? I don't know. You can make proposals here. And the other question is, do we need another interim before Berlin to just discuss results in a smaller group and be sure that everything is aligned? And I see people nodding here. Does anybody want to go to the mic?
Janet Eriksson. Yeah, I think I don't have currently any suggestion like how do you summarize all the results, but it would be good to actually do that to see like which candidate we might. I mean, I think you're right. All candidates need to update the results and show that. And as far as I know, Ingemar is planning to do, and he's planning for next IETF meeting to show full set of results for his stream. And I think interim will be really good, like Sunday or something.
Okay.
Xiaoqing, just a suggestion on sort of a summary of the results. What we can do is we can have the table. We basically have 3 sets of evaluation test cases, the wired, sort of the basic ones, the Wi-Fi ones, and the cellular ones, and then the candidates. What we can do is we can sort of fill in the most up-to-date, basically point to the most up-to-date presentation for each entry of the table. Quick update for the NADA solution. We haven't updated the algorithm since Yokohama. So everything we have shown for Yokohama for the basic test case is still up to date. And we're showing some update on the wireless test suits.
Okay. Do you also would need more discussion time in an interim for NADA, or do you think that's all solid and stable and can just be a quick update?
It's too early for us to tell right now, since we have not seen a need to update the algorithm yet. One thing we are aware that we're missing is the cellular set of test cases, but I have discussed extensively with Zahid. There are some barriers in doing that. So
okay. I mean, we don't have to decide right now. We just keep this in mind and then try to decide just a couple of weeks before Berlin. Okay. And then this is the agenda. I've just added this morning 2 little slots for Varun and Zahid because they sent me some slides on the status of those 2 drafts. But then everything else was announced previously. But anyway, if you want to bash the agenda now, that's your chance. If everything runs smoothly today, we have about half an hour at the end to discuss the common feedback format, which came up at the last meeting, and we have also prepared some slides for that. Okay, then Varun needs to rejoin the queue. Ah, there he is. Varun, you can speak.
Hi, everyone. So, next slide, please. Yeah, so I did a quick update to the eval criteria just before the deadline. As per the last IETF, we decided to add Stefan as the co-author to the document. I'm not sure if he's online, but he is going to update in the 0.6 version, update the jitter model with Google's proposal that was discussed a few IETFs ago. He was supposed to send in the text, but that didn't happen before the deadline. So I'm hoping this will get done in 0.6. There was some discussion with Zahid on the metrics definitions, if they should be in eval test or eval criteria. We decided that it would be nice to move them to from eval test to eval criteria. I'm wondering if anyone in the room has any opinion on if the metrics should stay in one place or should move to eval criteria. Else I will take a note of moving them. So the question is, does anyone have an opinion? If nothing, then I will just move them to from eval test to eval criteria. Okay, the next discussion was about video and audio sequences. This came up when we were talking about the audio and video traffic generation. So we have some uncompressed sequences. I think we had an email with the chairs a month ago about where to store them. They're currently stored on Alto's servers. I'm not, they will stay there for the time being, but if you need a long-standing URL, then we need a repo from somewhere. Maybe the IETF can help. I think there was an action item taken by one of the chairs to do that. I think there are not very. I think there's a question on Jabber.
Yeah, so the question, Jabber, is how long are these sequences?
Yeah, I think they're just 500 frames, I think, or 600 frames. At 60 frames. Yeah.
Churching is in the...
Xiaoqing, yeah, I have a quick comment. We need longer sequences if we want to run more meaningful results. We'll discuss this more extensively when I present the video traffic draft, but just a sort of foreshadowing comment related to the test video sequences.
Mozinati, as a NetVC chair, you can use the NetVC sequences if you want. We host them, and there's an extensive set. It's at least dozens of uncompressed sequences, and most of them are around 500 or 600 frames, but there's a few long ones too. And I believe Netflix is in the process of adding much longer ones. So I can send a pointer to the list of what's available now, and you can see if it's appropriate for your wireless testing. Is this for the wireless testing or for both?
I think for everything. They were supposed to be talking heads and so on and so forth with motion and more motion. So I think NetVC test sequences would actually be quite good because we could cherry pick some from there. But but your input would be appreciated.
I'll forward the info to the list.
Just a quick question: Where do you have those data? Are they on a private server, or GitHub?
They're on Mozilla's zif.org's private servers.
Okay.
They're not on the IETF
Okay.
any IETF storage. Yeah. But we can mirror them to wherever is most convenient for the team.
Okay, I guess that solves that problem. I'm hopefully waiting for Mo's pointers and then just incorporate that into the draft, and that should be a good starting point. At the last IETF, we had a question about UDP background traffic. I looked through the notes and I didn't find if we resolved it. So next slide, please. So I had a question. If we want to do UDP background traffic, probably we need to know how to generate it. Is it MTU size? What is the packet rate? And I just put together something along these lines here. But since I did not think about UDP background traffic, I was hoping, like one of the questions is, do we need it? And if we do need it, how would we generate it? So twofold question. And again, I'm looking for input from the working group on this.
As there's nobody in the queue to answer this question, can you post this on the mailing list again?
Sure. Okay, I guess that was the only remaining action items on the eval criteria. How do you want to do the rest of the slides? I think the next slide is related to the CC app interaction or app CC. So Stefan, Omar, and I had a few discussions since the last IETF. We are yet to submit a draft. We hope to do this by the end of April. I think that's the best we can say for the status right now.
Okay.
And the last slide was, I think, adaptive FEC. I don't know. You want to discuss this now, or do you want to go to Zahid's thing and then bring this up later at some point?
Only if you have something concrete to discuss.
I think the draft has been around for a while, and I'm wondering if there is energy to pursue it as a working group item, and that is my main question. We've made some headway, we've presented the results before, the last time being way back a year ago. But we're looking for guidance on, because I think the impression we got earlier was to keep it as a mechanism that everyone could use. And I'm okay with doing that, but for that, so the current draft does that. If you're not going to pursue that path, then we need to see how we would, we would need to rewrite the draft to include a congestion control algorithm, for example.
So I guess that's a question to the room. Is there interest and energy to work on this document? That's the question.
I guess no one's standing, I guess no energy, and we just keep it as is. And if there is energy at a later point, we would.
Yeah, so I have the feeling we have a whole list of working group documents at the moment, and just adding one more doesn't help us to get anything done quickly. And so in this case, I would propose to wait.
Okay. So I'll let it expire the next time until we have a chance to discuss this more.
Thank you.
Okay.
So it's about the updates, the recent updates we did on the eval test case draft. I think it was up for review, for a wider review, so that we can proceed with that draft. Next slide. So first, I would like to thank Shafiqul and Stefan for your reviews. It was really helpful. It brought up a couple of things, especially Stefan brought up a couple of things that we needed to discuss and adjust a bit in this version. So regarding the test cases, there is not the existing test cases. We didn't see any need for any change, and there was no such comment on need to change. There was more about clarification. We tried to do that. There was a missing. There was a comment about what the TCP test cases should have a default condition control, TCP condition control. So we picked this one. I would like to know if it is fine, or if you have any strong opinion to go for new Reno or QB. Okay, I think that's fine. You have comments?
Yeah, Kulevin. I think actually cubic would be more appropriate, and there's a draft out there, so it's easy to point to the draft.
Just point to the draft.
TCP cubic draft, yeah.
Okay. So is it alternative, or you want? So this is the default one. We can have an alternative,
Yeah, I would.
Saying this.
I would take TCP cubic as a default because it's a little bit more aggressive, and so it's probably the more interesting case to compare to.
Okay. So you would like to change it to cubic, okay?
So we have Rahun in the queue.
Pardon?
Yeah, I thought we already picked cubic. This was already discussed, I think, a few IETFs ago. I think we just forgot to put perhaps cubic on the. I think we already discussed it was cubic as default. So
I couldn't hear you. Are you saying we discussed to pick cubic and we picked the wrong one, or? We discussed to pick this one.
No, we discussed to pick cubic and we picked cubic. So I find it interesting. that we?
I don't really remember.
I think maybe we did not have a reference at that point, so we probably didn't.
Yeah, that's doable. And then we added I think there was a comment from Miria about a long time back, like when you're evaluating competing with TCP, you would like to see what happened to TCP flow, not only what happened to the congestion, Rmcat congestion control media flow. So we added that metric there, and then now I think all those things would be moved to eval criteria. And there are lots of needs and typos fix, and really I really like to thank the reviewer for pointing them out. Next slide. So there was some discussion about a couple of congestion control, and basically it was more about priority. How do you, when the flows are priority, what do you do? So we added a potential test case. It calls media flow with priority, and basically we extended the test case 5.4, and saying like, okay, you run the same test case, but you have a priority, and then the throughput and the priority is honored. So when you're in steady state, your throughput is basically related to your priority. And as I said, I think it is not clear. Like we're going to remove the definitions for matrices to eval criteria. Next slide. So there was a comment pointed out by Stephen Holmar saying like, okay, we're using audio video, but what about slideshows and screen content? Shall we be treating them separately? And the question was like, okay, is there any trace file that we can look into that is too different from the like traffic pattern point of view? Is it too different from what we are already doing? Because we have a test case called media pause and resume. So that's kind of like you pause the media, then you resume it, and it's almost if the media screen sharing content is something like that, it could actually cover that one. So I haven't received any comment back from Stephen Holman. So I think he's fine with the explanation. So we have not changed anything on that one. But if anybody has any other opinion, we can discuss that. Okay. So I think that was the last slide.
The integration with video traffic model.
Sorry.
The integration with video traffic model.
Okay, that point. Okay. Okay, so there was another point was like, okay, is there any clear cut between the eval criteria, media traffic model, and the eval test case draft? And there was some confusion like where exactly we draw the line. And the current solution, currently the eval criteria gather all the information you need to run to know more about the test environment, test requirements kind of thing. And then eval test define a specific test case that you would like to do. It also defines a structure where you can define a new test case. And then we have the media source model that defines like how you can have it's more about synthetic media model. And there are a couple of things that, okay, that's not.
No.
So the proposal is currently that in media source model, video source model, we design and define the models, and we also tell how do you realize the requirements in section 4, because section 4 in eval test defines like, okay, this is the video bit reference, this is the deviation from the rate request and all those things, and that goes as a section in video traffic model. So that was the solution right now. And then we will also try to see like, okay, if we can remove some of the text from eval test and actually point to the media, video traffic model, just for having all the discussion in one draft.
Xiaoqing, I just want to give maybe a briefer explanation on the relationship between the video traffic model draft and the test case draft. The idea is that we describe what's an expected media source behavior in a test case draft, just to keep the tests more realistic. And then for the video traffic model draft, we provide one reference way, actually two, reference way of generating generating such type of traffic sources. So it's about the how. So that's how we separate the two drafts.
Yep.
Okay. Okay.
Hi. Just going back 1 second to the screencasting case, and I'm seeing a fair bit of echo from the room. So excuse me if I'm a little bit stuttery when I talk. I would suggest we really do want to have at least one good test sequence with, thank you, with some slideshow type content. The traffic pattern and the encoding pattern is very different from live video, in that you'll have very minimal, almost null chain frames for if you bother sending frames at all, and then you'll have these big spikes of bandwidth that are needed for slide changes, typically. And that's a very different pattern, and that'll engender very different responses from the congestion models. So I think we really should have such a sequence.
Okay.
Yeah, also, Stefan on this point says in the Jabber that there's a difference, because when you pause the video, you can pause the congestion control as well and resume, but if you have a slide, so the congestion control will still go on.
Okay, so I think the way forward is like we look into the trace, and it would be really good if somebody can take these trace files and run run a test case and show us some results, like what exactly the difference on the where and how it differs from the other test cases. Then it's pretty clear to us, basically. Just discussing this doesn't really help me or anybody else, perhaps. So if Stephen can show some data, like how this is quite a large difference than what we are trying to do or what we have already defined, that would be really helpful to actually design the test case to address those kind of. And that was the comment basically we replied, because we don't know what we're talking about.
So Stefan, either you go to the mic and say something, or please go and talk to Sahid, or provide a video sequence that can monitor this case.
Okay, that's it from me. Any more comments or questions?
So sorry again on the video traffic model. So the relationship between the document, is this already cleared up in the documents, or do you need to have changes in documents to align them closer to each other?
I don't see like eval test need that much changes. Maybe a couple of sentences here and there, but it's more about video traffic model. Incorporating a section defining how you generate those kind of traffic.
Xiaoqing, as I remember, the updated version of the eval test draft has already pointed to the video traffic model as a source of let's say reference traffic generator. We probably need to update the video traffic model draft to point back to the test case.
And so I was rather asking, are you using, for example, the same terminology? Because the test cases, they define a certain number of parameters. Are you using the same kind of names for the parameters, and does it actually map?
That we need to realign the text. Yeah, we haven't done a conscious effort on that yet.
Okay, good.
Yeah.
It's your turn.
Hi, yeah, this is Xiaoqing. I'm going to give an update on the wireless test cases. This is pertaining to the wireless test case draft, but only two updates are all on the Wi-Fi section for the test cases. Next slide, please. So, well, this is just an outline since we're going to flip through quite a few slides. So it's good to break them into sections. So the first thing that basically I'm going to describe briefly that the main update is that we have updated the recommended test settings from 822.11g, which by now is really outdated, to 822.11n, which is the more prevalent kind of mode of Wi-Fi operations these days. And then I'm going to show the corresponding updated NS3 simulation results on the previous set of test cases we have presented back in Prague. That's IETF 93. And after that, two new test cases that we are proposing to add to the test case draft, basically, which will show, one is an extension of one of the current ones to show the behavior for a varying number of competing clients. The other one is designed to show the dynamic behavior of sort of the Rmcat flows in the presence of background traffic. Next slide, please. So this is kind of an overview. And then for the Wi-Fi network configuration, the updated configurations would reflect the 802.11n protocol. And these are the parameters that we have chosen to run the NS3 simulation. They basically reflect sort of one mode of operation in 802.11n. One thing that's worthwhile pointing out here is that we have picked an MCS index that reflects a raw data rate of 52 megabit per second. We could have chosen sort of a higher aggregate throughput, but there is some kind of a bug crashing issues in NS3 that's, that's why we picked the lower rates to operate with. Yeah. Next slide, please. So these are the key algorithm parameters in NADA. Most of the things reflect the default values stated in the draft, but just for our test suite, we have picked sort of a wider range of minimum and maximum rates, and that's kind of the only thing that deviates from the default value, and it's worthwhile pointing out. So these are the parameters we use to run the simulations. Next slide. Now we're going to flip through a few slides on the updated results for the test cases that are currently in the draft. The first one is, we haven't rerun the one which has the wired as the bottleneck, because that's more like a sanity check, and that obviously won't change if swapping a different mode of Wi-Fi operation. So this first test case that we rerun is for excuse me, is for multiple multiple downstream clients. So it's basically all from the access point to different Wi-Fi stations and running Rmcat flow. We have chosen to have 8 clients just so that in aggregation they have a reasonable, they converge on a reasonable rate. The main thing to observe in this graph, I suppose, is that we can see that if all the clients are going sort of downstream, there is not too much contention over the air, because most of the contentions only come from the periodic acts, which are fairly small, flows. So overall, even this is sort of running over the wireless media, we actually get a very good sort of convergence results, both for the rates and the queuing delay. The middle graph shows the queuing delay measured and estimated at the client, and no packet losses in this scenario. Next slide. And now for the flip case where we have 8 multiple, sort of 8 upstream clients. Now these are 8 sort of individual clients and all sending up to the access point. And here we see lots of airtime contention. That's why actually the results more or less reflect our previous observation that all the 8 of the clients have, sort of a wide ranging rates that they fluctuate over. It's very hard for them to converge on steady state behavior.
Jahid from Ericsson. Well, that's quite a lot of jumping in the rate, right? Bit rate. So my question is like, are you hitting some really saturated? Are you saturating the link so that this link might not be able to cope up with 8 clients or something like that? Have you tried with some less number of clients to see like if there is a possibility of convergence like the downlink or something? Because this kind of big jump in, I mean, this will be really horrible experience for the user, right? Because the real implementation, the encoder will not really be able to handle this kind of changes. I mean,
it is. Welcome to the real world.
Yeah, but,
I mean,
but
these
then,
are actually
then
not yet
my main
real.
concern is like, then should we be changing the test case so that we have less number of clients so that we can see like convergence, or it doesn't really matter?
Okay, so yeah, I get your point. So actually, later on, we're going to have one test case where we vary the number of bidirectional clients. So there, at least you will see that when the number of clients are, sort of underwhelming the network without, sort of without congesting the airtime, obviously things will run fine. What we're interested in is in seeing one, the airtime is sort of being saturated, right, with at least with the summation of the max rate from all the clients. So whether any congestion control solution can handle that, we actually welcome other solutions to try this out too. And our own understanding is that because all the clients, they don't have any physical sharing of the queue, and for Wi-Fi, it's a more unmanaged, sort of a random backup type of a contention over the air. We, at least our own guess is that it's very hard for individual clients to be able to, sort of converge nicely in the, as in the previous round. So this is mainly just sharing the observation, and obviously for the NADA solution, but we feel that part of the mechanism for Wi-Fi makes this, somewhat common, but that we actually welcome other people to try out new test solutions to either validate or,
I also like to see other candidates trying to do the same thing. And I mean, why I'm still standing here is like, because we also have an intention, like, can we create a subset of these test cases so that those are like really useful to look at. And if no candidate algorithm could do better job than this one, then I think this kind of test case is of no worth spending time on, because this is just a phenomenon that we have to acknowledge and that live with it.
Yeah.
So maybe you can say this is a test case, this is the results, and then.
Right.
So Ingemar just proposed in the Jabber that you look at how TCP would behave in this scenario, if TCP would be any more stable as a comparison.
Yeah, something like that. But that also requires like. So is that what we want to see, like how TCP and compare the results or something like that? Because we have not done that for other test cases.
I'm just echoing Ingemar, and I think it's rather to address if this test case is useful to see if TCP would do any better in this test case, and if not, it might not be useful.
Okay.
Yeah, and
that's
one
kind of
quick
a
comment.
good comment, I think.
I do not agree with the comment to say that if none of the algorithms works in this scenario, this is a useless test case.
Why?
At least it is my understanding is that people are interested in seeing how a collection of upstream clients compete and behave, right?
But
so I don't think that's a corner case test case. Maybe let me.
Yeah, it's good to have. I mean, for our own knowledge, it's something like that. But I'll not. If we cannot solve this problem, I'm not willing to spend more time on like looking at it and analyzing the results and stuff like that.
So I think the common sense on the mailing list was anyway that the wireless test case should not be mandatory to something that you need to show to actually move the document forward, but they still might be interesting.
Okay. So I have a comment on that one then. So as far as I remember, like this wireless test case was really important and then we discussed it before quite a lot before adopting. And the problem was like, then the main problem was coming like regarding the LT test case that we don't have a simulator perhaps implementation, or the implementers or designers of the algorithm, they don't know like how to run LT test case. But now we have a Wi-Fi test case and it is open source. So I don't see like for Wi-Fi test case there is a valid comment. For LT test case perhaps. So if you just, so what is the so I actually would like to revisit the comment what I have discussed in the mailing list, because if the implementation of these test cases is the only blockage to not include as a like mandatory, so then I think Cisco did a good job to open source this test case. It's available, right, somewhere that we can use?
Haven't shared the code yet, but this is like configuring a modular in NS3. So we haven't done anything. Yeah.
So
We'll be happy to share that as well.
Okay. Yeah. So then, the comments in the mailing list doesn't really valid for Wi-Fi test cases. So
I think the reasoning behind the comments, or the conclusion we got there, was that, I mean, the test cases are here to make sure that the algorithm is safe enough to run it on the internet. And my understanding is that usually in the wireless test cases, if the algorithm doesn't work well, the case is that it just doesn't get any throughput, but it might not hurt other traffic. So those test cases might be less important for just doing a safety check if it's safe to run the experiment on the internet. However, we can revisit this discussion.
Yeah, no, I mean, I'm just putting a fact, like the reason behind that decision and what we have right now. So maybe in future we might have some NS3 implementation L2 test cases that everybody can use. So but let's discuss in the mailing list. Perhaps. No problem.
Next slide, please. So this is just a quick summary of the previous pair of test cases where we're showing sort of the average rate and their standard deviation of the rate, as well as the average queuing delay for the upstream clients as well as the downstream client. So we see that basically on average, for the downstream clients, since we already saw the traces, so the average don't coming as a surprise. For the upstream clients, the point here is just to show that on average, they still sort of get a fair share of the bandwidth, but that's more the behavior of the 802.11 sort of a MAC. It has not too much to do with the congestion control part of it. Yeah, and then we do see a wider error bar, which reflects the standard deviations of the individual ray traces of each client. Next slide, please. And this is a case where sort of, having pairs of upstream and downstream clients. And here we're showing, I believe this is sort of 12 streams in total. So that's 6 pairs of upstream and downstream clients. Basically, it should be a collection of 6 traces of color dots for the upstream flows and 6 downstream flows. The same observation as we shared previously in Prague is that, actually 2, right? One is that we see that the collection of downstream flows in aggregation sort of converges on a tighter rate, and the collection of upstream flows do have wider variations of their individual ray traces. And the second thing is that there is unfairness between upstream and downstream flows, just because in 802.11 the MAC the access points has an equal opportunity of grabbing the channel as any one of the clients. So that's where the fairness comes in. And this one I can share sort of that we have also carried out TCP-based tests. So the unfairness part is there for TCP flows, just sort of upfront sharing what we have observed on the site. Yeah, and the next slide. This is just showing, again, sort of the collection of downstream flows and upstream flows in terms of their average and standard deviation of the rate, as well as their queuing delay. Next one. So, up to now, we've basically updated the results on the test cases that we have presented before. And now we're adding 2 more sort of variations of the test cases, just because we think they're interesting too. One is that for the case for bidirectional flows, now we carry out the same experiment, but vary the number of, total number of client streams. So for instance, the point that we shared earlier was for number of streams as 12 on this graph. So we sort of tried fewer number of streams as well as, higher number of streams, always pairs, bidirectional flows. So as we can see, and then we basically calculate the average rate and queuing delay across all the streams during their steady state part of the simulation. So we can see that, I guess not surprisingly, the rate per stream drops with the number of, as you increase the total number of streams competing in the same network, and also the unfairness between the upstream clients and the downstream clients sort of holds with a more or less the same amount of a gap, but in terms of ratio, it's probably a more drastic ratio as you increase the number of streams. And same thing for the queuing delay, especially for the downstreams, their queuing delay grows up pretty quickly when the number of streams increases over time. Next one. And finally, 2 new set of test cases designed to test the dynamic behavior of the streams when the background load over the Wi-Fi access sort of point has changed. The idea is that typically when we're using the access point, it's not dedicated just for video flows. There's always some background flow. So the way we test it is just sort of have a number of UDP background flows too, and at some point either sort of add them to the test setting or take them out from the test setting. So we have one set of cases where the collection of NADA flows drop their rate when the UDP flows start, and the slide after this one would show the opposite scenario where UDP flows leaves the network in the middle of the simulation. So what we can see here is that after they join, they do basically introduce kind of a step function type of change, reduce the rate of all of the NADA flows, and with some level of unevenness for what the flows can get.
There's a clarification question from Varun. Is there any loss on the UDP flows and on the NADA flows? Both
We haven't plotted the UDP flows for this graph. We can add that back. My guess is yes. Okay, next slide. Just basically showing the opposite scenario where the UDP flows stops at the middle of the scenario. So as we can see, basically the remainder flows do ramp up their rate in reaction to a lesser background, less congestion over the network. And these are bidirectional flows, by the way. Yeah. Next slide. That's actually the end of this presentation. Basically, in summary, we have showed an updated results using 822.11n compared to 11g from the previous set of settings, and we showed kind of qualitatively consistent results as before. Things that are worthwhile noting are that if we have a network that's majority is all just downstream flows, NADA actually works quite well, and we can still achieve a stable and fair bandwidth sharing. And whereas when in the case of all upstream flows, then because of the more over-the-air contention, sorry about the typo, yeah, basically we do see a worsened behavior for each client, and for bidirectional flows, we see basically an unfairness between upstream and downstream flows. The new test cases are designed to try out varying number of clients as well as dynamic UDP behavior, just so that we get a sense of how the Rmcat flows react to changes in background node in the Wi-Fi network. More questions, or should we move on to the next set of presentations? I'm going to stand here for a while anyway. So yeah, next set of presentations. Okay, yeah, switching gears now. Switching gears now, let's present some updates on the video traffic model with a new set of, a new collection set of trace data. This hopefully will help to respond to some of the questions that raised earlier, in the meeting for discussions. Next slide.
Sorry, can I interrupt you on the previous presentation? There is another question in the Java. Did you say how the background flows were modeled?
Those were UDP CPR traffic, and there were, I think I marked on the slides, there were 5 UDP flows.
Okay.
Yeah. Okay. So now for the video traffic model draft, basically we're going to give an update on the sync codec part. My colleague Sergio has helped to collect a new set of trace data and have also updated the sync codec source code along with the new set of video traffic traces. And then we're going to share some new traces that we have collected from 2 different mechanisms. One is a live video conferencing software, and the other one is just using the open source X264 codec. Next slide. So for the first part, the update for the sync codec, that's the open source tool that we have shared. We have basically moved it to a new URL, which is more official, under the Cisco account. And then also we have collected a set of video traffic traces, encoding them using X264. The things that, the motivation for us to do this was mainly to trying to get hold of longer sequences, since before we carried out this exercise, we actually looked through all the collection of test sequences that's being shared on the mailing list. Most of them are 10 seconds long and, 500 number of frames. That's perfectly okay for testing a video codec behavior. But what we have found out from our previously testing for the congestion control algorithm is that usually we want to run the simulations up to hundreds or several hundreds of seconds. So having a trace that periodically, having a content that periodically repeats itself every 10 seconds gives like an artificially repetitive behavior on the traces. So that's why we thought it would be nice to gather a longer video content sequence. Yeah. And so our first attempt, basically, and the other thing is that we want to be able to get video sequences with a higher resolution, just because the world is really moving towards, HD, 4K, even 8K, right, in the future. So we want to be at least a bit more open for higher resolution contents, at least 1080p. So these are the two main criteria that we have posted on the mailing list too, asking for inputs for recommendations for test video sequences. Now, but even before we got anything that we really wanted, we still went ahead and tried with two existing sequences online. One is Big Buck Bunny, and the other one is Elephant's Dreams. Those are both computer graphic type of movies. They're long running, but then as we'll show later, their contents don't really mimic talking heads very well. Yeah, so, but we at least went through all the tool chains to gather the video traces to share with people. Yeah, so next two slides. So basically, these are just sample frame size as well as the encoded PSNR values that's generated by the X264 codec at a target rate of 900K. We have tried out different encoding rates. The things to note is that first off, for basically the setting for X264 is that we have asked it to generate only a single iframe at the very beginning, and everything else is followed with P frames. But as we can see from the traces, once in a while there are really big P frames too that reflect sharp transitions in scene change. As I mentioned before, these are animation movie. And secondly, for some of the audience who are more familiar for the video codec side of things, PSNR reports on, anything above 50 or 60 dB is basically shows identical encoded results. And these basically reflect some of the presence of completely dark tile screens, etc. So those are really not natural video contents. Yeah. Next slide, showing similar things for Elephant Dreams. That's why we went back to the mailing list asking for, pointing to the need for gathering conferencing-like content. Yeah. But as a side note though, since people are interested in slide sharing type of content, we wonder whether this can maybe point to some similar behavior, or maybe we should just go ahead and also collect another type of video contents, let's say slide sharing. Next one. Yeah, actually, I have summarized everything here. So basically, as I mentioned earlier, we do have an motivation for gathering longer test video sequences, and I have already pointed out the problems with the two ones that we have tried out so far. But basically, this is more an open for comment thing. We wonder whether they can be somewhat useful for testing screen sharing type of application scenarios, or whether people would prefer to just gather some screen sharing content and carry out the encoding exercise separately. We do need more contents for conferencing like scenes, as well as maybe separately document and slide sharing. Mo.
Mo Zanatti. So like I mentioned before, we have NetVC has lots of sequences available, and they are already categorized by type of content, and there are lots of sequences for both conferencing use cases, head and shoulders content, and slide sharing, or even wireless display kinds of applications that would show screen content.
Oh, that's great. Yeah, I guess we're mainly concerned about the lens, so that's something to double check. Yeah, thank you. Next slide. So now, moving to the second part of the talk, we're going to share some other video traces that we have collected using different tools. This first set of trace is collected using a live video conferencing software. We basically obtained the RTP packet traces, and also since there's the there was a marker flag inside the RTP package, we're able to reverse engineer and put together the frame size for each that was generated from that live video content. This one was basically the video content itself was someone waving hands to, so it was a real conferencing content. And then what we did is that for the conferencing tool, there's a way to manually choose the target rates as a fake congestion control output, right? Initially at 1 Mbps, later dropped to 400K, and later reverting back to 1 Mbps. And I forgot to put it on the slides, but the resolution was 720p, for this one. So this is just an overview graph to show the kind of the step function like changes in reaction to the target rate change. And one thing that's worthwhile pointing out is some of the bigger frames, even though the content was more or less the same content, but when there was a target rate change, at least the codec in that conferencing tool did react by generating a few big frames, which we refer to in the draft as burst frames. Comment?
Yeah, Jahed. I mean, we are having, I can see we are having some codec experts sitting on this room. I would like to know if this is something that because this is not something that I have seen. And I assume like maybe there's like resolution change or something that's leading to this kind of thing. But is it like something that is pretty common in production level video encoder? I mean, does it happen pretty often? Because this is
Mosinati, I think what's being shown here, I think your confusion or your disagreement about what's being shown here and what you may have been observing in your test cases is that I believe Scream has a model of the video encoder that assumes the way it's going to operate under congestion, and I think your model is to back off on the frame rate, and this model I think is changing the resolution at those big jumps in the bandwidth that's available. So those two different strategies do lead to very different traffic profiles, because when you change frame rates, it's usually a much smoother profile. When you change resolutions, it typically is spiky like that, because there's either an iframe or a very large p frame at those boundaries. So I think that's explainable by the different assumptions of the two different testing models used.
But is it like running any congestion control in it?
No, as I said earlier, this is without congestion control, but the codec is unaware of that, right? I mean, the codec still just takes in, we kind of hack the conferencing tool to do it.
But in these charts, the codec is aware of the new channel rate, right?
So yes,
So,
I mean, the codec is reacting to the new rate.
The codec is being set at a target rate of 1 meg and then set at a target rate of 400K. And so those different settings for different codecs will respond in different ways. In this codec, it's responding by changing the resolution. In your codec, you're responding by adapting the frame rate. You're actually doing frame drops.
Yeah,
right.
we don't do those kind of things anyway.
Just,
But that's okay.
Sergio just said the resolution is fixed here.
Yeah, the resolution was fixed. But I'm also going to show another set of results from X264. If you were wondering about whether these are singular, burst frames or not, at least I'll show a different set of results using X264 in case you're wondering. At least we've seen, different codec behaviors. Maybe not the ones you use. I would be happy to get access to the ones you use too. Yeah.
Boberman, I wouldn't really say that if this is the same resolution all the time, I wouldn't say it's typical to see these peak when you change the bitrate. So something is not typical in this test.
Okay.
Miguel París Curento. I think that one of the most important factors here is the frame rate. I have experience about having a video frame rate with 2 or 3 frames per second for screen sharing with very high quality frames.
Mm-hmm.
So in this situation, you have a lot of peak of data because each frame is about each frame is generating about almost 1,000 RTP packets. So here we have a peak of a huge number of RTP packets, and from this situation, do you have some tests similar? Do you have some tests
You
similar?
mean for screen sharing? No, we haven't done that. You mean for screen sharing contents, right?
Sorry?
Maybe I didn't get your question. Can you repeat again? What
Yes.
was your question?
You
Yes.
do have tests for the situation of having only 2 or 3 frame per second,
No, we haven't tried that out. Yeah.
because it's another situation different.
Yeah, I guess you're referring to the slide sharing type of content, right? If it's 2 or 3 frames per second.
Yeah.
Yeah, I don't think anyone in the working group has tried or shared results on that yet. We haven't tested on that. No.
Okay. Thank you.
Ronnie Evan. My experience with video codec is that you don't know how they'll behave for changes, because you change the bitrate, okay?
Yes.
But you don't know what's happening internally, because
Exactly.
he can decide to reduce the frame rate or to reduce the resolution, because he cannot build
Exactly.
the same size of picture at 400 kilobit per second, and he made assumption what will be the best quality that adequate for this bitrate. So that's why you may see changes, but that's not all codec will behave the same. Okay, some will
Exactly.
behave differently. There's no rule about it. And on another thing is some codec may send every couple of seconds, they may send the full frame anyhow, because they want to allow people to synchronize again on the information. All these are internally of how
Exactly.
the codec is implemented, or how it reacts to different changes, and you cannot predict that how it will happen with different implementation of systems that doing video conferencing.
Yeah, we're not mapping the internals of the system. This is just observing the frame size, sort of as a black box outcome from one codec. Yeah. And, but actually, maybe let me take this opportunity to ask back to the working group one question about frame rate change, because right now, as I remember in the draft, we have kind of put on hold any efforts regarding frame rate change, but I'd like to sort of gather some input on whether people think it's kind of more realistic to change frame rates sort of instead of or in addition to changing quantization behavior. Because indeed, the codecs can be, we do not want to model its internal behavior, but the type of traces we collect, we can configure it differently, right? So that at least it's, sort of operating in one mode versus another. But we want to know people's interest in modeling frame rate change too.
Ronnie, you mean when you make change, when you want to make change the inverted frame rate or resolution, what you're doing?
Yeah. Well, let's say whether we allow the codec to do it before we gather the trace. Right?
So
Yeah.
I think that there were parameters in SDP that were allowed to do
Yes.
to do this compensation between. We took them out in RTC Web because they were not in the new because there was not real numbering for it. But system may again behave differently about what they conceive will be the better quality for the user.
Yeah.
If they need, for example, to reduce the bitrate, what will be better, to reduce the frame rate or to reduce the quality? Definitely, when you're doing, for example, if you're doing something that's like slides, you want the resolution. So frame rate
Yeah.
is not important, so
Exactly.
you may reduce it.
Yeah.
If you want to do
But
something
let
that's
me narrow
moving
it
more.
down. Let's not worry about, let's say, slide sharing type of content. Let's just focus on conferencing content for now. My question is more about whether, I guess it's more about, there are varieties of codec behaviors there, but is there, let's say, one typical codec that we can somewhat, sort of converge on, just like we picked some test sequences, right? If not, then what do you do for test evaluation purposes?
I don't have any suggestion. It's like if there
I
will
mean,
be
not for
one
you, for
behavior,
working group,
that's
yeah.
the same programmer wrote everything. For everyone.
Randall, you're on.
Hi. I realize this talks into the whole, we could have an infinite number of test cases. I think to keep things simpler, and also because I think it's also generally the better default assumption to make, we should leave the frame rates constant during and in any synthetic codec stuff we're looking at, adapt the quantization as a primary thing. My preference would generally be to keep the frame rates high and keep the quantization, let the quantization vary. And when you get, too far away from the target, you can adjust the resolution at the source in any sort of real situation, with frame drops being, sort of a safety valve available, but you don't want to drop the frame rate too much. So that's my general feel. I think it's simpler for the evaluation if we just try to keep it fixed.
I'm not sure if I get everything you said, but maybe as a confirmation, did you say that your recommendation is to keep the frame rate same or above a certain?
Simplicity. For simplicity.
Yeah, for simplicity, keep the frame rate the same. Okay.
I actually wanted to just almost same thing as Ranil said. Like, yeah, let's don't over-engineer our synthetic source model or try to understand what the real video codec, because what I hear from the experts here, like, it would be really different. If you change codec, if you change the encoder, or if you take the same encoder, change the configuration, you might get different behavior. So let's not try to create our semi-realistic video source model that will mimic everything. Let's fix on something concrete that we think like this is good enough and create our source model. If you are putting Rmcat solution in your production, you will like to try out with different encoder anyway. They'll figure it out, and perhaps then the implementers can actually tell us like, okay, this doesn't work, or this work, or this needs some modification. Let's don't over-engineer the synthetic video source model. Just targeting all those things.
Yeah, I fully agree. That's why I'm asking input from, people are welcome to look at the draft, and actually maybe we can also move on to the second set of traces too. But you guys need to at least pick something that's typical that you're all comfortable with, right? For instance, this one, if there's lots of objection to say this is not the type of behavior we should model, then let's point to an viable alternative. Okay? Yeah. Next slide, please.
So yeah, there is agreement on the Jabber that one should only change the quantizer.
Okay, so confirmation, change quantization for simplicity. Okay, yeah, but let's finish analyzing them first. Yeah, so these are just the zoomed in views from the previous trace, just to show the ray transitions. The things I wanted to point out are the kind of the burst frames, which were referred to in the draft. And by the way, the drafts were written after we've seen, not from this specific software, but from another software, similar behavior. So basically both for when the rates step down and step up. But obviously the thing to acknowledge is that these are artificial rate changes, right? They may or may not show up. You may not really have a sort of a 60% change in if you engineered your congestion control right. But this is just to show what might happen. Yeah. And next slide. And on the side, we have also sort of just gathered the steady state period from that relatively short trace, but we still have like 10 seconds of data for the steady state periods for both the initial 1 megabit per second, the middle part of 400K, and finally the 1 megabit per second. So we have gathered a few of the frame size distributions just to see how they look like. These are without the spikes, obviously. And I don't really have much sort of too many comments on the frame sizes. Aside from that, they look a little bit arbitrary, but somewhat, fits maybe a uniform model, maybe, we may want to gather more data, but this is kind of a typical frame size distribution that we see from this specific software. Go ahead.
Mozanetti, a question about whether or not these codecs are being operated in any kind of awareness of that there's a channel and there's feedback. Are you just setting it and letting it go and it has no idea whether or not there's any loss, or there's actually a simulation of a channel and loss events, and you're giving feedback to the codec about the loss events?
Yeah, so the test setup is that we're actually using a live conferencing software. The only thing that's different is that we hijacked the congestion control modular to feed it a constant recommendation.
By software, you mean just a codec by itself or a full
It's
RTP
a full-
system?
it's like
with
similar to
RTCP
Skype,
messages
let's put
coming
it this
back
way.
and feedback coming back?
Yes.
Everything.
Yeah, but except that, your network feedback doesn't really propagate all the way to the rate change, right? Because we have
Right.
we have fixed the rate, but it's a full running. Think about like you're running Skype,
Mhm.
and then, but then we, sort of fix the rates.
So my feedback, that's what I was assuming. My
Yes.
feedback was going to be that brings a whole nother dimension of complexity because the loss feedback going back to
Yeah,
a codec will manifest itself in very different profiles because some codecs will, if you have one single packet loss, some codecs may resort to full IDR frames, and some may be more tolerant and just accept lossy situations, and it may take an accumulation of many losses before you get the iframe.
Yeah.
Some codecs have very advanced resilience strategies and may never send an iframe.
Yeah.
So that really gets into details of different codecs. It would be very hard to generalize. If you want to pick one, I would suggest picking one out of a common application like WebRTC browsers, and picking one of those and using that as the test harness for your simulation.
yeah, and that's good comment. I fully agree that we don't want to get into modeling the codec behavior. That's why we've confined our draft, at least for video traffic source. Just use it as a traffic, sort of a traffic generator. We don't even care about reaction, and we don't even want to get into all the modeling of loss behavior. Also because this is for congestion control, right? It's not for, not for transport in general. Yeah. Next slide. So just to recap the behavior, the transient behavior we have observed from this set of traces is that it does introduce burst rates when the rate, let's say in the presence of significant rate upshift and downshift, and the burst frame size is kind of 5 times, let's say 5 to 7 times the target size. And the steady state part of the behavior, we just sort of shared some of the frame size distributions that we have captured from this, like 10-second durations for the steady state. And the amount of variations around the average or the target rate is around 28 to 40%. That's kind of the number we're interested in capturing in our draft. Next slide. So now a second set of traces that we have collected using X264 using the zero latency setting. Here, basically, we have again tried different rate shifts using 1 megabit per second as a kind of a reference point and chose rates to either below or above it to shift to 1 meg or the other way around. The video content here, I forgot to post on the slide, but the video content here is 720p. It's called Johnny. It's one of the test video sequences, sort of from I think actually from one of the evaluation links shared by people here. I'll add the content. That's a sort of common talking head type of sequence. So basically, the things to note here is that let's take the 400 kilobits per second to 1 megabit per second example. Basically, there was a gray line which shows the traces for encoding that sequence at 400 kilobits per second throughout, for the entire duration. I think that was a 250 plus frame type of sequence. And then the upper greenish line shows the frame size trace for encoding that trace at 1 megabit per second. And the blue one shows when we configure the codec so that it knows it will encode the first 120 frames at 1 meg and then need to switch without introducing an iframe to 1 megabit per second. So the entire thing is no iframe. We just want to, again, try to model how codecs react to a requested rate change. So here we see somewhat different behavior, right? In the sense that when we when the rate upshifts, we do see a bigger frame, and whereas when the rate downshifts, there's no burst frames. So that's the first thing to note. The second thing to note is that after we upshift, at least for 100 frames or so, the frame sizes are actually different from a steady state behavior if you were just collecting it from encoding a frame, basically encoding the codec at a constant rate of 1 megabit per second. These are the two main observations. Okay.
Okay,
Yeah.
sorry, just clarification question. In this, this is the one that you show as a config file, right? In the beginning of the slide.
Yes,
So here resolution can change.
no resolution change.
Okay, so what was the other one that we talked about? We talked about,
The other one, there was a confirmation from Java. I believe that was from the my colleague who helped to gather the live conferencing result. There was no resolution either, change either.
okay,
Okay, yeah.
Ronnie, and just for clarification, was the switch from 400 to 1 megabyte and for one was done at the same frame, at
Yes.
the same point?
Yes.
Okay.
And when-
Very quickly, I'll just note that, while this is interesting about X264, X264 was not originally designed as an interactive codec, and this could be very different for a different implementation. It's more the measurement of the implementation, not of the codec per se.
So not even for their zero latency configuration? I was just curious.
The zero latency configuration, my understanding, not being an expert on X264, was a later addition to X264 that they added.
It was one of the flags we added. Yeah, sort of not we added, we turned down, and what they said in the configuration tool
Right.
is
Right. So
Yeah.
the point is the base codec they're using is was not designed for or optimized for this initially.
yeah, on that, I mean, maybe I will not put that kind of configuration in an interactive video application that you used, but yeah.
okay. So I was just curious, will people be interested in gathering some traces on your own codec? Like, for instance, there are so many experts here. Yeah, maybe Zahid, since you have the codec and you observe so much.
Doesn't need to be own codec. As Mo said, I mean, you can just take the OpenWebArt
Yeah, but you can,
WebRTC implementation and then you can generate, because
yeah,
that's like lots of people using it. So
right.
that should be
So
pretty fine
would there be people
representation.
interested in doing that too?
Sorry?
I'm just asking, since there's so much interest, are there people interested in gathering some of the traces like that too?
Yeah, sure.
Okay, thank you. Next slide, please. Yeah, let's just try to flip through the results. These are similar, but basically showing a different step of rate transition. For instance, this is from 600 to 1 megabit per second. Next, 800. One thing to note is that by the time you get, let's say, 20% rate change, the bursts are no longer that obvious. Yeah, well, it's sort of, we don't really see big burst frames. The next one, and these are sort of using 1 megabit per second and going up to 1.2 megabit per second. That's 20% change. Next one, to 40% change, and next one to 60% change, basically 1.6 megabit per second. So this is kind of the range of a rate that we have tried. Next one, please. So, and just to summarize, this is the collection of a steady state rates. Basically, these are encoded using a fixed rate and removing the initial part of the frames. So, and then we have calculated again the frame size distribution at each target rate. For instance, the one shown on the right is with a target rate of 1 megabit per second. For this codec, actually, the steady state behavior do look more or less Gaussian or, gamma. We haven't started working on fitting the statistics yet. So next slide. And these are just additional graphs showing the frame size distribution at different rates. 800K, 1.2 megabit per second. Next one, sort of, lower and higher rates all the way through. Yeah, we can flip through them. Yes, next slide, please. So basically, just to recap our observations for this set of traces, basically what we've seen here is that the frame size after rate transition kind of one thing we did notice is that after the rate transition, the frame sizes don't really overlap, right, with the constant, the traces generated using a constant rate throughout. So we don't really see it converging to the previous set of frame sizes also over time. And that's kind of an interesting behavior. So at least we feel like, if we're using trace-only type of, sort of generations, we might be missing that type of behavior. And secondly, in terms of the transient part, one, the rate upshifting is smaller in steps, let's say 20%. There's no significant burst frame behavior, whereas if it's very high, then it's a big step. Then we again observe burst frames for upshifting, and the steady state behavior, the distributions we've seen from this collection of traces are more Gaussian-like, and the fluctuation, sort of the range of change, is about 16 to 22% around the target rate. Next one, please. Oh yeah, so basically this is a summary. I think I've more or less, summarized the key points throughout. Maybe in the interest of time, we can move on. Oh, actually, I do want to point to the last regarding input from the working group and reviews on the draft. We appreciate all the comments being made here from the meeting, but we also appreciate people looking into the draft and pointing to specific things. Since apparently there are quite a few people with in-depth codec knowledge. So it's good to capture that, not just here, but also in the draft. And we like to have recommendation for video sequences, looks like also codecs, maybe even codec configuration, or if there are people who are more comfortable doing these type of things, we welcome to get the traces too, or even the analysis. Yeah.
So Randall just said in the Java that he would try to grab traces for VP8, VP9, and Open H2 64.
Oh, that's great. Question?
Quick question, Michael Mala, Cisco Systems. I probably should have asked this at a different venue, Shashini, but on these rate changes, it almost looks like whatever it is now operating at the new rate is probably doing it via some token bucket thing that's averaging rates and replenishing over a reasonable amount of time. And it looked like the time constants were like 3 seconds or something like that. So, so even when you reduce rate downward, if they're resetting the token bucket and giving you a lot more bits, it might make sense that some of these frames immediately after rate change have a higher, frame size than what will soon come afterwards. So my question is, how often, how long are these frames? Are there like only the first 2 or 3 frames after such a?
Yeah, our observations from the traces are typically there's like one big frame and a few smaller frames after that, and then it becomes more fluctuating around the target rate.
Yes, I'm thinking that when you're doing this, there's some token bucket being replenished, and it's thinking, wow, I've got lots of extra bits for the next couple frames, and it's producing large numbers of large frame sizes. So I'm just wondering, just from a median filtering kind of standpoint, would a more meaningful result, or at least one that is more expected, be simply that you just discount 2 or 3 frames after the frame change? I mean, we're talking about 40 frames a second. You just discount those frames in some way and get a more meaningful or more representative overall result. I'm just posing that as a question. I just just thinking about it real time here. It just seems like this particular codec is doing something that when you change the rate, it's replenishing the averaging mechanism for the rate, whatever that is. I'm presuming it's something like a token bucket, and I'm presuming it's over a relatively long period of time because of the distribution of your frame sizes, right? And if a simple thing is just discounting the first couple frames after a frame size is something that makes sense. So I just posed that to a question as a group. I don't know the answer to that question.
We need to move on.
Yeah, okay. Switching gears again, now let's move to solutions. Yeah, sort of, this is an update on NADA as one of the solutions in the working group. We're going to present a stability analysis for the kind of the basic mode of operation for that algorithm, and also show some analysis and simulation results on the impact of different feedback intervals for NADA. Next one. Outline we can skip, as I just mentioned, some stability analysis. A quick update on the draft itself. We have updated the draft. There's no algorithm change from the previous version. The main section we've added is on feedback requirements in section 5.3 as a follow-up to the previous working meeting decision. And then we have addressed the fairly extensive review comments, both from Stefan and from Jahi. So thanks a lot for both of your sort of input. And then also, I do want to take this time to point out that Ingmar, right, has also provided input on the mailing list too. So that's appreciated. And finally, and Mira, you provided the review comments for the previous round. So yeah, and then finally, some minor adjustments in terms of notations and fix various errors as the draft kind of converges over time. Next one, please. So for this, we can now talk about stability analysis for the NADA feedback control loop. Apologies ahead for being a little bit math heavy for the slides, but we can, this is just actually a rewrite of the rate update equation when we consider the NADA operation in its kind of the most basic form, where sort of the gradual rate update part and also reacting to delay only when there are no presence of petty losses, which we believe should be kind of the main mode of operation for this algorithm. And then the equation here is just a rewrite of the equation from the draft, just to make it more sort of LaTeX friendly. And the next slide, we jump directly to basically from that rate update equation and also from a fluid model for the queuing behavior. At the bottleneck, we can derive the whole feedback control loop in the Laplace transform. We do have a backup slide for people who are interested in the derivation from, sort of from that rate update equation all the way to this feedback control loop in Laplace, sort of the transfer function form. And but in the in the interest of time and for people's interest, we skip that to we move that to the backup slide. So here, the things to point out is that basically for the R zeros in these equations correspond to the system at equilibrium. And then for a single flow, the R zeros and the network capacity would cancel out. Next one. So given the open loop transfer function, two quick observations is that, so basically this is kind of a frequency domain representation of how the system responses to input signal. We can see that at low frequency, that's basically the DC behavior for the system, and the transfer function kind of reduces to a ratio, and that ratio is determined by the R, like for different flows, let's say for different flows sharing the same bottleneck, that ratio is sort of captured by the R0, which in turn is basically proportional to the priority setting we choose as well as the maximum rate. So that's kind of like a frequency domain proof that our system does ensure weighted bandwidth sharing that we have mentioned a couple of times in the draft. And now the other thing is when we look at the high frequency reaction of the transfer function, we can see that basically it reduces to this sort of approximated simpler form. And from that, we can derive to a guaranteed stability analysis for the criteria in the red boxes. Basically, the portion which has the exponential term and the RTT term sort of are guaranteed to have like a confined amplitude for a given scaling function, and from that we can basically derive the stability criteria, and that's important for us to choose the correct choices of kappa and eta in ensuring system behavior for system RTTs below the our designed parameter tau. Yeah, and people can refer to the draft in our rationale in choosing those parameter values in the draft. Next one. Now, so much for at least having some insurance on the stability for the NADA control feedback loop. With that, we can actually use that also as a tool to look at how different feedback intervals potentially impact the system. Next one. So this is just a frequency, sort of a body diagram on that open loop transfer function. The thing to point out here is that the critical sort of the crossover frequency is the one around kind of in between the two feedback intervals we've chosen. Basically, we just wanted to show that for continuous system, whereas in our own system, at the end of the day, we're really operating in a discretized version of the system, which is driven by the feedback interval, since we have discrete feedback interval. So if the feedback interval, the frequency of the feedback interval is significantly sort of lower than the crossover frequency, then the continuous system model is relatively it's a relatively okay approximation. Whereas if the feedback interval, for instance, at 1 second is already exceeding the crossover frequency, then the continuous system model itself doesn't really hold very well as our tool for analysis. That kind of gives us some guidelines on the range of the feedback interval that we should be interested in. Next one. And this is just to show that the transfer function itself or the stability behavior doesn't change much for different choices of bottleneck bandwidth. The previous one was for 600K and this one was for 1 megabit per second. Next page. And now we show that from the transfer function, we can easily calculate the step response of the closed loop system, basically how it reacts to a step size change in the system. And the continuous one and the discretized version match fairly well when we have a very frequent sort of when the system is discretized with very fine time slots. So here, this one is discretized with 20 millisecond intervals, then its behavior, basically the continuous and discretized versions match pretty well. Next one, if we sort of increase our step size at 100 milliseconds, we start to see some difference in behavior, but they still sort of qualitatively match each other. If we keep flipping through, the next one is for 20 millisecond. Next one, by the time we get to 500 milliseconds, we don't really, I mean, although both systems still converge, the overshoot in the discretized version is obviously much higher than the continuous version. And that points to kind of higher overshoots in the actual system too. So next page. So this is just a summary. So from the previous step response functions, we can calculate the settling time of the step response, and that sort of points to the convergence, like how fast the system reacts to change. So as we can see, if we increase the feedback interval, which corresponds to the time slot for discretizing the system, then the settling time does increase over time. And by the time we get to half a second, it takes longer for the system to converge, which means slower responsiveness and actually also more overshoot in the sort of in reaction to change. And those are undesirable behaviors. Next page. So these are like numerical side of the analysis for how the system behaves for different discretized versions. We can now try to confirm that using simulation results. So many traces, but very similar. The idea is that if we flip, so we have actually carried out both NS3 and NS2 simulations, and also carry them out for the same test case as specified for the first test case in the test case draft, but now using different feedback interval for the NADA protocol. So if we start from here and move on from 20 milliseconds to 50 to the next one, 100. So in the process, people can see that, especially for the NS2 based results, it takes longer for the system to converge to a steady state over time. So I'll do that. Oops. What should I do?
Just close it.
So which one should I use?
The arrows.
This one.
Yeah.
So yeah, I don't know whether it was clear. So basically, as we move, let's say from 20 or 50 milliseconds, it was very fast for the system to react to step changes in the bandwidth, whereas by the time we get to 20 and 500 milliseconds, it takes significantly longer for the system to converge to steady state. And by the time we get to, obviously, feedback intervals of 1 second or 2 seconds are a bit insane, and they do show that we have some unstable behavior in the reaction too. At a different propagation delay, we more or less see the same behavior. I'm just showing sort of 3 different feedback intervals at 20 milliseconds, 200, and 2 seconds. Again, by the time we get to 2 seconds, that's really not where we want to operate at. So maybe as a summary slide, we're just showing that the transition.
So there's a clarification question in the Jabber. Why was the jitter different in NS3 than in NS2?
Yeah, so the NS2 implementation, the test case was implemented using a physical change in the link rate, whereas in NS3, we're using basically the available bandwidth change was introduced by introducing a background UDP traffic. And that turns out to the delay measurements basically observed by the algorithm are slightly different. Yeah. So that's why those two results are corresponding to each other. But as we can see also here from the convergence time, because of the wigglings in the NS3, they don't really, match exactly. Yeah. So the NS2 one, I guess, is slightly more interesting. At least, again, we confirm the change in sort of increasing convergence time. And this is convergence time measured for the transition when the available bandwidth drops from 2.5 megabits down to 600K. So we chose to calculate the convergence time for different feedback intervals. And our recommended setting is at 100 milliseconds. It's kind of a trade-off between how fast you want to react versus how much overhead you can introduce to the system. So that leads us to the summary page. So for this presentation, we have shared some stability analysis for the feedback control loop of NADA, which guarantees its stability for round trip times of the system below 500 milliseconds. We have also shown qualitatively matching results from both numerical and simulation results. It shows that basically the system does remain stable even for feedback intervals up to sub-seconds, but then the response slows down with increasing feedback intervals, and that's why we recommend the feedback interval at 100 milliseconds as a trade-off between the two, basically between overhead and the response speed. And for future work, we're interested in kind of investigating a little bit deeper look into that convergence behavior for the two different type mechanisms of bandwidth changes. And also, now that we have the tool of stability analysis, we can also try to use that tool to get an idea, to help guide parameter choice and network setting. I guess people are exhausted with questions now.
Yeah. I'm trying to figure out because Ingmar has some comments on the driver, and I'm trying to figure out he wants to speak on the mic.
No.
Sorry.
Hi, I'm new to this. Hope you hear me well. Or I was asking about this comment that you have some get an additional jitter on when you use NST3 and you have a sort of background UDP traffic. And what the question is that you might get the jitter because you have your NADA packets or RTP packets controlled by NADA sort of in between UDP packets, and you get some either get ahead of the UDP load packet or behind the UDP load. Then given that you are quite low thresholds, that you might get sensitive to this, or is that the reason to a jitter?
Has someone captured the question better than I did? It was sort of
maybe I should ask
sorry.
I wasn't
Is a jitter from NADA is it because it's behind UDP packets? That's the question.
You mean for NS3?
Yeah.
Yes. Because basically the way we introduce available bandwidth is by introducing UDP background traffic, which means that the delay measurements from NADA will not be perfect, right? Will not be as if you are running it through a physical link chain. Did that answer your question?
Yeah, that's confirmed my question. Okay. I wonder if you can get other traces of traffic that might give more sort of disturbances to the NADA algorithm, given that you have a very low threshold for the algorithm. I believe it's a 10 millisecond threshold for the delay or something like that. Can you imagine some other traffic traces?
By the way, sorry, I was. Jahi, did you get what he was asking, or?
Yeah.
Okay. Sorry,
maybe
we can try to exchange email.
Yeah, I will try to speak slowly. Then, and could you imagine that you have
the audio wasn't going through very well?
Could they introduce more disturbances? So.
Okay. in this case, go back to Java, please, Ingmar.
Yeah, okay.
Maybe it's about like getting more disturbances, more noise on the back feedback channel, so that you might actually get some traces or cases where you cannot have like 100 millisecond
Right.
feedback
We
interval or
we
something
haven't
like
tried
that. Is
different feedback intervals, but we did show previously results on having disturbance on the backward channel, if that's what you were
That
referring
was
to.
the question.
Yeah. Okay. Thank you.
And there's one more question. How does NADA depend on synchronized clocks from peers in Java?
Sorry.
How does NADA depend on synchronized clocks at both communicating hosts?
The algorithm does assume that sender and receiver are relatively synchronized. That's how we calculate queuing delay. Is that the question? Oh, yeah. Does that
I
address
guess the question is, how bad is it if it's not synchronized? Did you look at that?
We haven't.
Thank you.
Okay. Thank you.
Okay, thank you. Yeah. Hi, everyone. This is a very, very quick update on couple congestion control for RTP media. My name is Shafiqul, and my co-authors are Michael Wetzel and Stan Yassin. So this is reflect what we have changed from version 00 to 01. We have shown results on both couple congestion control with NADA and couple congestion control with GCC. And now we have added text on how to apply couple congestion control to GCC. And we also updated the variable names based on the latest NADA draft to make it inline. And by looking at the IETF RTC web transpose documents, where they mentioned about the prioritization levels, very low, low, medium, and high. And we have made reference to it to make it inline as well. And we thank Karen's for her feedback, and we incorporate Karen's comments in the latest draft. And also, like, based on her comment, we marked the passive version which we put in the appendix as highly experimental. So this is what we did from version 00 to 01, but now I'm a bit open to suggestion from the chairs, like would like to know what they want from us. But
yes, so our understanding was that basically the draft is ready.
Yes.
So we could probably move to working group last call. If somebody disagrees, you can go to the mic now.
You were talking about like incorporating some results for Scream. What happened to that one?
I think like we will only move on with GCC and NADA because we don't have enough time to work with Scream.
Okay, so maybe then,
but if the chairs like decide
maybe
that
then this draft need to stop. Well, not to stop, but wait for like the final decisions, or on what algorithms are this working group is proposing, or?
No, because the way it's presented in the draft is that you have a general mechanism, and there are two samples how to apply those mechanisms to proposed congestion control mechanisms. So it's no problem to finish the draft as it is and then apply it later to Scream as well. Okay. The other option, if you would like to see Scream in there, and the authors don't have manpower to do the work that's needed behind, because it's not only the text in the draft, it's all doing all the simulations and results for it. Yeah. Then if you have manpower to do it, we can probably wait for your results. Or I assume the authors would be happy to incorporate it if you have input for it. But if you don't have cycles to do it, then the document is just ready as it is.
Manpower, good question. I cannot commit to anything right now. I need to think about that one. That is good to know, like this is ready.
I mean, we can definitely wait a couple of weeks for a working class call for you to figure out if you would like to contribute.
I was
here.
even in the impression like the there will be incorporation, like you'd like to see how it behaves when with the stream or some other algorithms and stuff like that. But that was perhaps my wrong impression from previous discussions. But if you want to go into last call.
Okay, good.
That's it.
Thank you.
Thank you very much.
Good morning. David presenting an update on shared bottleneck detection for coupled congestion control with Michael and Christian and Simona. I'll just talk about the changes we've made going from 03 to 04 and then the promised quantitative experimental results, a summary of them anyway. Of course, in a month or two, hopefully, they'll be in a paper that we've submitted. Our revisions, we included a section as asked outlining the feedback requirements in the 3 possible scenarios that this can work in. We've referenced Jung's convex Hull algorithm for estimating clock skew. As a reference, I use a stripped down streamlined version that adopts some of her things, but it's too much to sort of include that sort of thing in a draft. It's better to cite a paper, which it will be soon. And the other suggestion that we've added was that if you don't want to put in a clock skew estimation algorithm, it will work as it is, but using a small averaging period, basing the skew estimates only on the previous time intervals t and not using the frequency estimator, you get a noisier but still reliable mechanism. And that's been added to the draft as well. Looking at the statistics, we're using a simulator because that way we can see what's actually happening at the bottleneck to compare what the determination is with what the reality is. In this case, we use TMX background traffic that in this case takes about 90% of the load in different cases. And each iteration has different traffic at the bottleneck. So the bottlenecks are very different from run to run. And the flows send at different rates. Now this is a look at the positives in determining the bottlenecks. The black one is how it is exactly as it's written in the draft with the threshold method and with a clock skew estimation one. In this particular simulation, there was clock skews ranging from plus 10 parts per million to minus 10 parts per million across the different sources. Then the same method, but dropping the frequency estimator. And in this case, you see as far as positives go, it's quite a similar result in this particular case. It's not as similar when you look at the negatives, but then if you use a more advanced method, as we've always said, that this is an area of ongoing research, the draft should have a simple method that this is how you can group things, but there are more advanced methods, and in the paper we're working on, we have a clustering mechanism, and just sort of taking the same thing one step further, you can improve your results by using a more advanced clustering mechanism. Now, just working on the last T and not adjusting for clock skew at all, and no frequency estimator, you do get higher positives, but that to some sense be expected. The penalty is with the negatives in this case. Now looking at the negatives, no bottleneck, detecting that there's no bottlenecks. Okay, if you use the short without clock skew adjustment, but the short mean one, yes, you lose out a bit on your accuracy for detecting that there's no bottlenecks. Your error bars are bigger. As I said, it's noisier, but it still is reliable. So that is an alternative to putting in a clock skew adjustment mechanism. Again, looking at the straight mechanism from the draft, the threshold one, it's good in terms of being reliable for detecting that there are no shared bottlenecks when there should be. And if you use clustering, you do slightly better. Now, with these mechanisms, the positive and negative results were based on if you detect the bottleneck and whether it's positive or negative. They weren't marked as negative if there was a lag of up to 10 seconds. It was just measured as a lag to finding it. So in this case, this is a lag to detecting a shared bottleneck starting, which, because you're dealing with summary statistics, it does take a few seconds to happen. And if you're not doing clock skew adjustment, but that alternative we've put in the draft, it's slightly worse for that and noisier. The lag for detecting that a bottleneck's gone away that you're sharing, similar around the 4-second mark on average, but it varies depending on what's happening at the bottleneck. I mean, you could have a very strong bottleneck where there's a huge amount of traffic being compressed, your queues are at maximum, or you can have a very slight bottleneck that fluctuates around a bit. So that's why you see wider sort of confidence intervals. They span the entire range of experiments in this case. And if you don't use a clock skew adjustment but just work on the last T, then it takes you a bit longer to detect the bottleneck's gone away. Okay, so the preferred way of operating this mechanism is as it is in the draft, and put in a clock skew adjustment mechanism. Your favorite one, we've referred to that convex hull one. And of course, when I publish the paper, you can use a streamlined one that I've been using here. But the alternative of just working on a very short mean for your skew estimate and relying on the averaging does work reliably, but not more noisily. Okay, and the conclusion, as we were asked by the chairs earlier on, is that we think the document as it is now, it has the information necessary to do a proper implementation of it, which we have trialed and ready. Thank you.
Yeah, just as a background info for the group, but we did this already a while ago, I think. This document is experimental, that always was, but our charter says this should be proposed standard, but we adopted the charter and it now also says it's experimental, and that's what we want to go for.
Thank you.
Yeah, I mean, like, I didn't hear any comment that anybody thinks this is not ready for working plus call, so we will run that very soon. Yep.
Thank you.
Oh, that's actually me. Okay, so and then we started the discussion on the feedback requirements in the last meeting, and in the meantime, and the decision was that we want to collect requirements, what's needed for a common feedback format between the sender and the receiver, or the receiver and the sender actually. The drafts have all been updated. So on all of the candidate drafts, including the shared bottleneck detection, you find those requirements. However, we also asked the authors to give us a brief summary so we can have the discussion here, what we want to do from here on. I just will run very, very quickly through the slides because we put the slides We tried to put the slides early in the web, so you maybe had a chance already to look at it. So this is the first one regarding NADA, where you basically have 3 variables which are very specific to NADA. And that's in line with what Xiaoqing said previously about the feedback rate. We also have a summary slide at the end, so we will have an overview there. Then we got feedback from Stefan here. And he has two different phases here where he needs different kind of information. I think the next slide gives a little bit more feedback on which information are actually needed. So that's very, very basic information like packet identifier numbers and arrival time and send time and so on. And these are used to basically estimate the loss rate and the throughput. Scream. The feedback is based on arrival timestamps, and I just move on very quickly. And also we have a couple of slides in here where Ingemar explains how this feedback that is needed by Scream could be mapped to existing feedback format in RTP. And for Scream, I think that's what you're also using right now, right? You don't define an own feedback format for your implementation?
The implementation has its own Scream feedback that we previously has spread.
Okay, but like he shows that it is possible to map all the feedback in existing formats as well, and gives more details on it. And that's again about the rate. I skipped just very quickly to get to the summary slides. We left all the slides in here so you have them and can look at them as background information. And then if we come to the shared bottleneck detection, actually the feedback is also based on one-way delay measurements, but there are also some statistic that needs to be transmitted. So this is slightly different than from the other candidates.
Dan Ramashkanu. So one of the slides included a comment about unnecessary overhead because of duplication of fields. Actually, everything that came after RFC 3611 is a reorg and modularization. So actually, you need to use either 3611 or any of the RFCs that followed up. You don't need to do both. So you actually avoid this duplication of fields.
Yeah, and then also for the shared bottleneck detection, we have basically, or David is coming.
Yes, sorry, I did symptom update. There was one statistic missing from here. It just mentions delay. We also use loss, or the proportion of loss as a statistic to fall back on when it's very high and the other statistics aren't valid.
Okay, so we will update the slides for the record. And then shared bottleneck detection has the 3 different nodes where they do the calculations either at the sender or receiver side or part of the calculation. I think this was the same question for the candidates as well, where to do the calculation. And for the candidate, everything seems to converge that all the calculation will be done at the sender side. Here are the different options as well. Okay, and I think this is more useful for discussion maybe. So we try to just, what we got from the slides here, put on one slide what is the needed information. And at the moment, it doesn't look like the candidates need to use the same information. But if you look a little bit more detailed, it's basically the same information because we have packet loss a couple of times here on the slide. We have bandwidth estimation, which is done maybe slightly differently. One time it's done based on timestamps. One time the best bandwidth estimation is done at the receiver side and sent back to the sender and stuff like this. And the question is, can we converge from here? Does it make sense?
Xiaoqing, I just have a quick observation. I noticed that looks like some of the feedbacks recommended by other schemes seems to be more detailed. So if it's okay to use more, basically the field values recommended in NADA could be derived by those more detailed information. For instance, our aggregate congestion signal is a combination of delay and loss, etc. So I just wanted to point out that it's okay to derive from more information to generate the value. Potentially, it's okay, yeah, to generate the values we want.
Stefan, you're on.
Oh, thanks. I just wanted to clarify that the packet identifier is mostly there so that we should be able to perform or compute our bandwidth estimate on an aggregate of all the streams that we are sending, and not as much to compute the loss rate, although that's of course a possibility too. I also want to clarify that the packet send time is typically already known at the send side. So if we agree on having this on the send side, then of course we don't have to send the send time back to the sender.
Stefan, a question. I mean, the packet size is also available on the sender side, right?
Right.
So basically, same as this screen like arrival time stamp. That is what you need. Packet,
right?
Yeah. So that's
arrival time and other identifiers.
Yeah.
Okay, Arun is also in the queue.
Yeah, actually the next slide is what I found interesting because these are things that can be encoded. The interesting bit was, I think, slide 21, where I think maybe this is the first thing that people need to find convergence on is the feedback interval, and then decide how you encode the packets, because if you want to indicate less or more information, depends on how many packets are in that interval that you're reporting on. So I think that is a better discussion to start with in terms of feedback interval, and then decide. Then we know which metrics we want to measure, then we can encode it in a more compact way as a second or a third step. So I think some discussion on what would be the preferred feedback interval would be actually pretty good.
So, Jahed, Varun, are you saying like, okay, depending on the feedback interval, the requirement on the information from the candidate could change?
Well, that could be the second bit if we actually agree on the interval, but how to encode the information on the previous slide is basically dependent on what is the like granularity of information you need, right? So if you need list of received RTP packets or the arrival timestamps of all the RTP packets in the last feedback interval, that's dependent on how large the feedback interval is.
Yeah.
So I think the slide 21 is more important than slide 20 to begin with. If we can find convergence on what the minimum feedback interval would be, because if you want something at a higher granularity, you could always insert that information every 10th report or 6th report or something like that. But
Mia Kuhlin, yeah, so I agree to the last statement. I think we don't have to agree on one feedback rate. We could think about some kind of signaling mechanism which requests a certain feedback rate, but whatever is needed for the candidate. But if we get the minimum feedback rate, then we can figure out what's the maximum number of bits we want to send, and then from this value we can figure out how the feedback can look like. I think you agree, right? Yeah.
Mozamati, I was curious whether or not those those feedback interval times, whether they should be absolute, or would it be more intuitive to think of them in relative to RTT? Why would the solution candidates care about these fixed time frames? Is it based on media in encoding absolute times, or is it really about relative RTT intervals? Where are the numbers? Where do you pick 100 milliseconds? Is it based on 5 frames worth of media, or is it based on you think that the typical RTTs that you're seeing are around 100 milliseconds?
Xiaoqing, I can provide the answer just for the NADA solution. As we have presented earlier, the values are derived because so first off, our algorithm, the reaction time is independent of RTTs below a certain level, so that it's kind of RTT independent. And secondly, then the numbers we have picked is based on the trade-off between overhead and response time, kind of the convergence time of the system. So that's why it's an absolute value. I hope that answers your question for one of the solutions.
It actually seemed like it complicated the way I was thinking about it. It's actually multiple factors that are feeding into your feedback interval. One of them is RTT. One of them is reaction time of an encoder, which is, I assume, absolute values for the encoders that you're looking at. And then a third one is, I missed the one in between.
Clarification. The input to that decision, there's no RTT. We're assuming round trip times below a certain level, then our feedback loop is the way it reacts is independent of RTT of the system.
I remember the third one. It was a balance between overhead and reaction, right? But I would think that the purpose of having the feedback interval is to make sure that you're not sending too many bits in the in the window, in your congestion window, right? And so I would think that RTT would be a critical part of that.
The congestion control is not a window-based key. At least the one that we're offering is not a window-based key. And the overhead is more like, obviously, we can always work with more frequent interval. So let's say even if you do per packet info, we'll be happy about it. The overhead is more about the constraints, right? So the real decision is how fast you can react to the system. And obviously, you want it to be fast. The faster, the better.
Like as a practical example, what I'm thinking of is if somebody's streaming on a home network, right? You wouldn't want Rmcat congestion control to bottleneck what they can stream on their home network, right? But if they're streaming across the internet, then you would think that, okay, Rmcat would be a little more cautious. So I was expecting that RTT would factor very heavily into the feedback intervals. If your RTT is 1 millisecond, I wouldn't expect that there's a...
Mike, you need to go to the mic.
Maybe a clarification again. This is not the case where you get to send, let's say, even if you have a very short RTT, you get to dump all the data to the network because it's source constrained. So your maximum rate is upper bounded. That's why it's not sort of RTTs below a certain level for us. We're independent, we're indifferent to that value.
Yes, I also wanted to make sure that people understand that the RTCP can get lost. So, so the feedback can get lost. So whenever we think about the feedback interval, that's also something that we need to cater for. So if some message, if something is critical, you can't like pick which interval to send it on because maybe that packet might get lost. So there are things. If you pick and choose which interval to send things on, there are some constraints to that. That's all.
Yep. Stefan?
Yes, thanks. So I just wanted to say that, or add to what Xiaoqing said, that the feedback rate, at least for GCC, is not really related to the RTT. If we have a lower feedback rate, that just means that it will take us a longer time to detect that we're sending too much, and that will result in longer queuing delays. If we have a shorter feedback rate, we can detect it earlier. But the feedback or the RTT is connected to the way that the congestion controller behaves, so that it acts moves more slowly if the RTT is long. I just wanted to clarify that.
Thank you. Go ahead.
Hi, Brian Trammell. So I did hear one thing that you said on the clarification questions, that yeah, so since this feedback isn't basically driven by Windows, and I don't think any of these are, the RTTs are probably not relevant, but it would still be good to have those as comparison in this table for the tests from which these parameters were derived, right? Because you also said that you're making an assumption about the maximum RTT, and I'm assuming when you go outside that window, then things get weird, and it would be good to know what those are, and it'd also be good to know sort of like if those are comparable for the 4 different schemes. So that doesn't really feed back into the feedback interval because the feedback interval, but there's a little thing missing, I think, on this table.
Jahed. I saw like Ingemar send out a slide that has like the effect of longer interval and the feedback rate. So if it is a for stream, if the interval is longer, it just like means that it will be functional, but you will get the throughput will be low. And whether it just depends on RTT, maybe Ingemar can comment on that one.
Okay, and also asking about the dependency on RTT, and RTT is not the key design factor here. It's rather that you have a media rate that is sort of if you have a high media rate, you need a higher sort of feedback frequency. At really low media rates, it's not that important with a high feedback rate.
Was it here? Okay, thank you.
Okay, David Hayes, just a comment on SBD's time there. It's not dependent on RTT, it's dependent on how many packet measurements you have over that interval. So that's the base interval in the algorithm. You need enough measurements of packets to be able to calculate the statistics. If it's too small, you don't have enough packets to calculate it. If it's bigger, you can calculate it better, but then you delay how long it's going to take for you to detect the bottlenecks in the end as well.
But you basically say there's no problem with stability here.
No.
Xiaoqing, just a quick answer to the previous request on RTT information. One is that the test case draft, I believe, has specified the range of RTT in the form of propagation delay. You can multiply it by 2. That's kind of interest to most of our tests here. And secondly, for the NADA solution, our detailed collection of slides do report on the conditions, sort of the RTT information related to the numbers we derive. Thank you.
Wasn't any clarifying question. Feedback here means all types of feedback, or specifically, rate update feedback. Just rate updates, or information that you want to feedback in order to do a rate update. Is this the only type of feedback you're talking about? Because this feedback is also critical for repairing the media, right? And that was my point, that this needs to be very tightly bound to the RTT, because in a very low latency network, you want the repair to happen very fast. You don't want to wait hundreds of milliseconds to repair media. And so if you're like, the practical example is streaming locally versus streaming wide over the internet. If you're streaming locally, an Rmcat solution should not be, having dropouts of 100 milliseconds in order to repair the media. It should be reacting instantly. Your streams should always be pristine. If you're streaming over the internet with higher RTTs, then it's okay to throttle your feedback in order to avoid clogging the back channel with your feedback. So that's my point about it's strange to not see RTT factoring into this and having absolute feedback intervals.
And Xiaoqing, just maybe clarifying answer. So far, the discussions and the analysis are for rate adaptation only since this is for congestion control. And I totally agree with all the concerns on loss repair. The question is whether this is in scope of, or out of scope for this working group. And secondly, it's okay to send regular, let's say, to specify a regular feedback interval for the purpose of rate adaptation, but potentially send, let's say, loss indications as soon as you observe it. So, but my own proposal is to consider them separately, and probably loss repair is not the thing we discuss here.
I mean, the takeaway from this comment would be like, how often do you anyway get RTP feedback? And, you know, if we try to minimize it, but for a different mechanism, you need a lot more feedback, then there's no reason for us to minimize the feedback anyway.
Hi, Miguel Paris of Curento. I have a general question for all proposals, and is if you are taking into account the performance of these algorithms, because from my point of view, it's quite interesting for building more scalable systems. So there are measures about the performance, or are you taking into account the performance either in the design of your algorithms?
Sure. I'm not sure I got it completely.
Are you taking into account the performance in the design of your algorithms?
Performance of what?
The performance of the implementation of these algorithms.
So we have
CPU performance and the overhead in the network.
So overhead in the network is definitely something we need to consider. CPU performance should not be a problem for the feedback format, right?
I think that is quite interesting, taking into account the CPU performance for some systems.
Yeah. Yeah.
Please
So-
go to the mic.
Maybe a clarifying answer. The calculations for rate estimation is very lightweight and very, you know, sporadic, sub-second level. That's why we're not measuring CPU for that portion of the calculation. Did that answer your question?
Yes. Did I look the performance figures on the CPU, how many CPU cycles? Perhaps not in detail, but 2 of these proposals are already implemented out in the internet. So if you're interested, you can look into that one. So these are 2 of the solution. The GCC and Stream is implemented in real, OpenWebRTC and Chrome implementation of WebRTC. So 2 of these are there. So if I would really like to see, like, if there is the implementation that has some performance issue, that would be really like to know. But so far, I'm not sure. Like, I have got any feedback on that. No.
I would also assume that CPU performance is not a problem for us because it never showed up so far.
Sorry, why the CPU performance is not a problem?
Because the calculations are just not that complicated that it would reach any boundaries.
Yeah, but I am talking about system that does not transcode at only forward packets. So the relative weight of this algorithm could be more significant than in systems that are transcoding and so on.
So I'm still not sure, but we have to take it offline. We have to take it offline. You can go back to the mailing list and send an email.
Okay, thank you.
Okay. The question about the feedback format. So do people think there is actually an opportunity to create a common feedback format here? And I think in this case, I go back to the previous slide. Or what's your current feeling? What does the group think are the next steps here?
Jahed, I can talk about all the 3 candidate condition control algorithm, not about SBD. I see if I hear from Xiaochen, there's this data analysis could be derived from the more detailed information, and GCC is the same. And I think Scream, we just need two things. So I think there is a possibility that we do it. So I think Ingemar did a good job when he divided the feedback algorithm is a functional and an enhancement. So for enhancement part, like we would like to have ECN, we would like to have points bit. So it would be really to address also some sort of comment like Varun did, like, is it like, what are the, I believe these are the, these are the feedback the algorithm reads for functional purpose, right? So I see there is a convergence. I see there is a need, and Scream says like we can do this XR block graph, but that would be really good to have a new feedback message to do that. And I'm more interested is like that also means like I'm assuming everybody having a sender-based adaptation. Currently, that is not the case. I mean, I heard from Stefan and from Xiaoxing like it's no problem with moving everything to sender-based. If we have a sender-based system, I think this is possible. But I'm not sure about this video. Sorry, I didn't look into in very detail, but I can only take care of. My comments is only for the candidate.
Yep.
Yeah, so I think the main thing I'm looking at these feedback requirements and the intervals, the most important bit that I think people need to agree on. And then I think this is a good summary of what information needs to go there. So I think those are the two pieces of information that is needed before we can move forward. And I think if we pick a feedback interval, then that would be one step in the right direction. And then people can run their congestion controls with that to figure out if that makes sense or not across all the test cases.
Yeah, Kulevin. To add this point, I think there are two options: either picking one feedback interval for everybody, or trying to have some kind of negotiation at the beginning of the connection and say we need feedback from the group. What's the right thing to do here?
Yes. So when it comes to interoperability, I think we can do negotiation on feedback intervals. So say like in one direction you have a X algorithm, another direction a Y algorithm. They have two different feedback requirements, and they can negotiate it. That's completely fine. I think Born pointed out a good thing. Like we need to do something about the feedback rate. But I do agree with you. Like it's a negotiable thing. I mean, we're not talking about a symmetric solution. If a Scream talks with the Scream or not a GCC talks with, that's not an issue. Here we are talking about more about is the Scream start to talk with NADA. What is the feedback interval we need? Then I think that's negotiable. And the session setup.
Yeah, I'm going to extend what Mirja said. In addition to the fact that you could negotiate this at the start and independently in each direction, depending on what's going on, I think all the other either we need to agree on a fixed value, agree on some sort of negotiation or something that's codec, at least congestion control specific for the time being, or agree that that depending on other factors like the bandwidth, as was discussed, there was some simple algorithm for deriving what the feedback rate provided by the receiver is.
Xiaoxing, I guess this is a question maybe back to the other two solutions. Are there any limiting factors for the feedback intervals? Would any of the algorithm would prefer to have, let's say, some higher feedback interval, sort of less frequent feedback than lower? My understanding is that we're really being limited by the overhead of the system, right? Is there any other limiting factor to see, basically to see less, to see information being bunched up less frequently? Because if everyone, given the possibility, if all the solutions prefer to operate at faster feedback, then there's no need for negotiation. We'll just pick the minimum feasible. Why negotiate? I didn't get it.
if we get the minimum, there's no point in negotiating, of course. If it's not, then we're talking. So I'm talking like it's possible to negotiate when things are not as expected. And if it is expected, then I think it's, yeah. But the thing is like the frequency of, I mean, we're also talking about RTP. So the frequency of the feedback will be calculated from the session bandwidth. So you don't want to dedicate all your session RTCP feedback session bandwidth to your condition control so that nobody can send an PLI or a feed which was needed, because that is also a factor here. And maybe you can also look at the performance if it is sending frequent large feedback is a performance issue or not. That's another question. But that's why if I'm fine with having a less frequent feedback, I should do that so that I don't block any other necessary feedback. Because in the real-time system, on this kind of system, it's not only condition feedback that is coming from the receiver. There are other kind of feedbacks, and we have to distribute the whole thing, whole RTCP bandwidth across all the feedbacks that's supposed to be coming from the receiver.
Just a quick observation that it looks like the core of what's really being important to be feedback, especially if we're going to all sender side CCs, is ACK and time format. So I suggested contact. Make sure keep AVT core and XR block in the loop, so that we don't reinvent any wheels or or do anything that that there was already a direction for giving those ACK formats in those groups.
I think here in Rmcat we are only discussing what is the common things, commonalities, and what can it do. But if it is an RTCP message, it should be in the other working group, right? Rmcat is not going to have the feedback format here, but this is just a discussion about knowing what is required. So.
Yeah. And there was a question in the Java room about if we already agree that everything will be sender-based. And I can also say on the site meeting we had on Tuesday morning about the framework, there was large agreement that this is better, and everybody is moving to sender side. So probably yes.
I don't know if you can hear me.
Yeah, we can hear you.
Good. One thing to remember about high feedback rates is that typically this will be used in an interactive form where there's traffic going in both directions. High feedback rates implies you're competing with the media traffic going the other direction. And so you're stealing bandwidth from that, not just it's not a free lunch.
We don't want to have condition control for feedback.
So again, how do we move forward from here? Does anybody wants to go ahead? I mean, like Stefan's document already describes a format which doesn't fit all the needs I think we have right now. So do we want to keep working on this document and make it fit to all the candidates? Is this a proposal?
That sounds reasonable to me, Jahed. And basically that also means like if we are going to all, well, let's take this slide and bit more. Try to find more similarities like you already tried to do, and then work on Stefan's draft, I guess. And the Stefan draft has some criticize about this common what was it? Transport agonistic sequence number and stuff like that. I think that has been addressed, and in this other slides, like they said, okay, some sort of sequence number or sequence number RTP timers could work. So that's like that is not a problem anymore for Stefan's draft, I guess. So you can just condense this information to similarities and work on Stefan's draft.
So my proposal would be in this case to have a small design team that can sync up. We are telephone basically, and then bring the results they have back to the mailing list. And I think it's pretty clear who has to be on the design team. Say, do you want to take the lead on this side? Because you're nodding already, you're heading, you're sitting there. Okay, so just, contact the people and set up a call or something like that. Cool, thank you. Anything else? Oh, we're already over time. Okay, so we're done. Thank you very much and see you next time. Actually, I don't see you next time, only in the audience. Have fun.
If you're going to share this,